Today we shall look at a few examples on relative motion. So, the first example that we have here is, there is a man who is standing in an elevator which is going down at an acceleration with an acceleration of a. So, this acceleration here is shown, and he has a coin in his hand which he holds up just next to the top of the elevator, the roof of the elevator, and from there he drops this coin. We are supposed to find out the time taken by the coin to reach to the floor of the elevator, the time when the coin hits the floor. So, we will try to do this question in two ways. We will try to do it without using relative motion and then with using relative motion, and we shall see how both the ways will give us the same answer, but how using relative motion the question becomes much simpler to work with. Okay. So, we shall work first of all in the ground frame. When we say we are working from the ground frame, what do we mean? We mean that the observer who is observing this whole thing happening, the coin being dropped by the man standing in the elevator which is going down with an acceleration a, that observer himself is standing somewhere on the ground which is at rest. So, let us say this is that observer who is standing here on the ground on the side, and he is observing all this happening, the elevator going down with an acceleration a and the coin being dropped by the man. Okay. For this observer, understand that the coin will fall down with an acceleration of g, the acceleration due to gravity when after it is released, and the elevator will also be going down with an acceleration a, so that by the time this coin falls down and reaches the floor of the elevator itself will go down a certain distance, isn't it? Because it itself is accelerating down, right? So, what we can do here is we can assume that, let us say it is in a time t that the coin hits the floor of the elevator. So, the coin reaches here, but within that time, let us say the elevator goes down a distance y, so that as seen by this observer, this coin as it hits the elevator floor has travelled a total distance of h plus y, isn't it so? So, the condition that we can use here would be that the time t in which this coin which is falling down with an acceleration due to gravity g travels a distance of h plus y, in the same time the elevator goes down a distance y while it is moving with an acceleration a, and we can form equations corresponding to this, right. So, in the ground frame, that means as seen by a person standing on the ground, for the coin the equation will be we can write the displacement equation in terms of the acceleration, the second equation of motion, s is equal to ut plus half at squared, which for the coin would be h plus y, the displacement, is equal to ut. Now, if we assume that the moment when this observation was made, the moment when the coin was dropped from the elevator top, the elevator itself was having a velocity of u. It could be any velocity, we can just assume it for now, because we shall see after a while that this term will cancel out. So, if we assume that it has a velocity u at that time, the ut term will be just ut and then plus half gt squared. This becomes the equation for the coin to for the time that it takes to hit the floor of the elevator. For the elevator at the same time, in the same time t, the displacement of the elevator downward is y, is equal to, the elevator has the same speed at that time, so the same ut, and plus half at squared. The elevator is moving down with a. Observe here that we have taken the downward direction positive while we have written these equations, so that the downward displacement is positive, the downward velocity is taken positive, and the downward accelerations are also taken positive. Now, we can solve these two equations, and if we look at both of them, we see that it will become easier for us if we subtract the two equations. Rather, if we subtract the second equation from the first, then the term ut will completely cancel out. This term y will also cancel out, and we will get h on the left hand side is equal to, on the right hand side we will have half gt squared minus half at squared, isn't it, which we can simplify to write as half into g minus a into t squared, and from here then we can find out the value of t, the time in which the coin will hit the elevator floor, which will be 2h by g minus a and square root of that. So, this will be our answer for the time. Now, let us do the same question from the frame of the elevator itself. What do we mean when we say we are working in the frame of the elevator? It means that now we have another person who is standing within the elevator. Let us say this person's friend is standing along with him in the elevator and observing everything happening. So, in the elevator frame, what do we understand? What will happen, or what will be the quantities now? From the elevator frame, that means when the elevator itself is at rest, right? This is how we observe, or this is how we define the frame of reference. The frame from which the body is being observed, that frame, that observer is always considered at rest. So, while the elevator itself is considered at rest, we say that the velocity of the elevator goes to 0 and the acceleration of the elevator that itself goes to 0. For us, for the observer, now the elevator is completely at rest, and if the elevator is at rest, do we understand that as the coin is dropped from the top, it has to just travel a distance h in order to hit the floor of the elevator if the elevator is at rest, isn't it? But since we are working in the elevator frame, we have to find out all the quantities now associated with the coin with respect to the elevator. So, the velocity of the coin with respect to the elevator, the initial velocity with which the coin would be dropped, would be the velocity of the coin minus the velocity of the elevator, which will be 0. Understand that if the elevator is at rest and the person is standing in the elevator and he holds this coin in his hand and he simply drops it, releases it, then the initial velocity of the coin would be 0, right, as seen from a person standing within the elevator. So, this is what we are getting here. Also, what will be the acceleration of the coin in the frame of the elevator with respect to the elevator? It will be the acceleration of the coin minus the acceleration of the elevator, isn't it? The acceleration of the coin is g downward minus the acceleration of the elevator is a downward. So, the relative acceleration of coin with respect to the elevator or in the elevator frame would be g minus a. This is an important thing to understand. And then, since the elevator is being considered at rest now, the displacement that the coin has to have in order to hit the elevator floor will be just h. So, once now we use the second equation of motion, we will just have s, which will be h is equal to ut, the u term will be 0 now in the elevator frame, plus half a, the acceleration of the coin with respect to the elevator will be now g minus a, right. So, this is the u that we have used here, this is the a that we have used here, into t squared. In the elevator frame, this is what the equation we will get. And if you look at this equation carefully, this equation is nothing but the same as the equation that we have obtained here. To obtain this equation here in the ground frame, we had to first write the equations for both the coin and the elevator, and then we had to work with those equations. But here we are getting this equation directly in one single step. So, see that it is easier, it is less time taking to work through this question in the elevator frame rather than working in the ground frame, right. Do we understand that if we are getting the same equation, the answer that we shall get from here will also be the same, through root of 2h by g minus a, right. So, see that working in a relative frame, in the frame of a body which is moving itself, sometimes solving the question becomes easier, it is less time consuming and hence it is faster for us. Let us look at another question now. So, the question is, rain is falling vertically with 15 meters per second. A cyclist is moving eastward with 5 root 3 meters per second. In order to protect himself from rain, how should he hold the umbrella? So, the angle theta that he should hold the umbrella with, like this is what we are supposed to find out. Okay. So, do you understand that while the cyclist is moving in the rain, the velocity of the rain as seen by the cyclist will be different from the actual velocity of the rain, right? We have to use relative motion here, and when he get the velocity of the rain as seen by the cyclist, it is in the direction of that direction in which the rain is falling with respect to the cyclist, that the cyclist will have to hold the umbrella, isn't it? So, essentially we are supposed to find out the velocity of the rain with respect to the cyclist, which we know from the basics of relative motion, as we have studied in the previous class or the previous video. It is the velocity of the rain minus the velocity of the cyclist by definition. So, we have to get this value now. For that, we can just take the help of a vector diagram for vector difference. This is the direction of VR, the velocity of the rain, right, and the cyclist is moving in this direction. So, this is the direction of VC, the velocity of the cyclist, and if we have to do VR minus VC, which we know now from vector addition can be written as VR plus minus VC, we need to draw the vector minus VC, which will be like this. Just opposite to the vector VC will be the vector minus VC. This is the vector, and now we have to add the velocity of the rain with the negative of the velocity of the cyclist, and we understand that the sum of these two vectors will come out to be this using the triangular law of vector addition. This will be velocity of rain with respect to the cyclist, and it is in this direction, that the cyclist will have to hold the umbrella. He has to hold the umbrella like this, right? So, we are supposed to find out this particular angle, the angle theta, that he should take the umbrella making an angle with the vertical, right? Theta is that angle. How do we find out theta? We can take the help of this diagram here. Can we say from this diagram tan theta will be the opposite for this angle theta? This length is the opposite. This length is the magnitude of the negative of the velocity of the cyclist. Magnitude would be the same as that of VC, and VC is given to us. VC is 5 root 3. So, it will be 5 root 3 divided by the base. The base length is this, which is nothing but the speed of the rain falling down, which is given to be 15, right. So, 5 root 3 by 15, which comes out to be 1 by root 3. So, we understand that theta here will be 60 degrees. That will be the answer. Let us look at one more question here. The next question is, a man standing on a road has to hold his umbrella at 30 degrees with the vertical to keep the rain away. So, that means this is the direction of the velocity of the rain. The rain is already falling at an angle with respect to the vertical, right. Now, the man throws the umbrella and starts running at 5 meters per second, and then he finds the raindrops falling on him vertically. We are supposed to find out the speed of the raindrops with respect to the road, that is VR, and the speed of the rain with respect to the man, moving man, while the man is moving in the rain. So, let us understand this question. Rain is falling at an angle. So, initially when the man is standing, simply standing, he will have to hold the umbrella in the direction in which the rain is falling, right. So, if he is holding the umbrella at 30 degrees, that means the rain is falling at 30 degrees. Now, when he throws the umbrella and starts running in a particular direction, he finds that now the rain falls vertically with respect to him. Now, this is important to understand, that while the rain is falling at an angle like this, this is the velocity of the rain. In case the man starts running like this, Vm, when we try to find out the velocity of the rain as seen by the man, we will have to do that by, we know that velocity of rain with respect to the man by definition is velocity of rain minus velocity of the man, which is velocity of rain plus minus of velocity of the man. So, when we draw minus velocity of the man like this, this is minus Vm, and we try to add it with Vr, this is the direction in which the man will find the rain to be falling, which is even more inclined, isn't it, with respect to the initial direction. Initial direction was only 30 degrees, now this angle will be even greater than 30. So, we understand that if the man really wants the rain to be falling vertically as seen by him when he starts running, he needs to run the other way around. That means, he needs to run like this, the way we have drawn here in the figure. So, he needs to run opposite to the direction of flow of rain. So, the rain is falling like this and he will be running in this direction, opposite to that. So, that when you draw minus Vm like this, then when you try to add Vr with minus Vm, there is a possibility that your vector sum comes out exactly vertical, which is the condition they have given in the question. They say that Vrm, the velocity of the rain as seen by the man, is now absolutely vertical. So this is the figure then that corresponds to the question in hand. Okay. Now here in this case, do you see that from this figure, Vm is already given to us. Velocity of the man with which he starts running is given to be 5 meters per second. From here, that means this length is known, this particular length is known here, this will also be 5. Can we find out Vr, which is the velocity of the rain with respect to the ground, and Vrm, which is the velocity of the rain with respect to man, both of them? We are essentially supposed to find out just speeds, not directions. So we can directly use this right angle triangle here that we are getting here. For finding out Vr, see that we can use the trigonometric ratio sine. We can write sine of 30 is equal to the opposite by the hypotenuse. The opposite for this angle 30 degrees is the magnitude of minus Vm, which will be Vm itself. So 5 divided by Vr, isn't it? The velocity of the rain, which is the hypotenuse. And from here we can easily write Vr is equal to 5 by sine 30. Sine 30 we know is 1 by 2. So that becomes 10 meters per second. That's the speed of the rain falling down with respect to the ground. Understand? This is just Vr. And in the second case now, to find out Vrm, which in this triangle is actually the base of the triangle, can we use tan of the angle 30? So tan 30, which by definition is opposite by the base, opposite is Vm, the magnitude of Vm, which is 5, by the base, which is Vrm now. So from here we can write Vrm is equal to 5 by tan 30, which we know is 1 by root 3, right? So this goes up and makes it 5 root 3 meters per second, right? So this way, just by using the figure, we can get both the answers easily. Let's look at one more question now. This is related to the riverboat problem. It says a river which is 200 meters wide is flowing at a rate of 2 meters per second. A boat is sailing at 10 meters per second with respect to the river. So this is VBR, the speed of the boat with respect to the river is 10 meters per second in a direction perpendicular to the river. So the direction of the boat with respect to the river is perpendicular to the river. And then we have to find out the time taken by the boat to reach the opposite bank. And also we have to find out how far from the point directly opposite. So if we take this point as A, the point which is directly opposite to A will be B, and let's say the boat, because its velocity will be in a direction like this, it will reach the other shore somewhere here at the point C. So we are supposed to find out how far from the point directly opposite to the starting point does the boat reach the opposite bank. That is, we are supposed to find out the drift suffered by the boat, right? So those for whom this topic is new, they can just go back to the previous video and revise where we have done all this, the riverboat problem, the rain man problem we have discussed in the previous video. From there you can get the theory well, and now we are going to use that theory here to get our answers for this. So we are supposed to find out the time in which the boat crosses the river as well as the horizontal drift suffered by the boat. If we just recall from what we have studied in the previous class, we understand that the velocity of boat with respect to the river, which is by definition velocity of boat minus velocity of the river. From this expression, this is the basic expression for definition of relative motion, isn't it? Relative velocity. From here, can we write velocity of the boat? The actual velocity of the boat with respect to the ground will be velocity of the boat with respect to the river plus the velocity of the river. Velocity of boat with respect to the river here is given as 10 meters per second across the river, whereas velocity of the river itself is 2 meters per second along the river. So we understand that we need to add these two vectors to get the net velocity vector VB, velocity of the boat, which will come out in this direction, isn't it? Right? But for the sake of convenience, because we are not supposed to do complicated things with respect to this question, they are simply asking us to find out the time and the drift. We can just keep this velocity of the boat in its component form itself. This component is across the river, VBR, and this component of velocity of the boat is along the river, VR, right? And we can use them directly to solve our question. So for the first part, to find out the time in which the boat crosses the river, Do we understand that it is this velocity component, the VBR component of velocity of the boat, which helps it cross the river, because this is the velocity component perpendicular to the river? So can we simply say that the time taken by the boat to cross the river will be the width of the river divided by the velocity perpendicular to the flow of the river, which is VBR in this case, only VBR, right? So can we just write this as 200 meters by VBR is given to us as 10 meters per second. So 10 meters per second, this will come out to be 20 seconds. The boat takes 20 seconds to cross the river. And then the second one, to find out the drift. What is drift by definition? The drift is the displacement of the boat along the river in the time in which it crosses the river, right? So the time in which the boat crosses the river we have already obtained. All we need to do is multiply this time t with the velocity of the boat along the river, which is nothing but the velocity of the river itself, isn't it? This component of velocity of the boat is along the river, VR. So VR, right? Just substitute the values, 20 into 2 meters per second. So this becomes 40 meters. The horizontal drift of the boat would be 40 meters, this distance d. So directly using the basic concepts, we don't even have to remember the formulae that we have derived in the theory when we were discussing this. If we understand the figure well, directly taking help from the figure, we can get our answers. Let's take one more question. So this one says that there is a swimmer who wishes to cross a 400 meter wide river flowing at 4 meters per second. His speed, the swimmer's speed with respect to the water, is 2 meters per second. So VSR, velocity of the swimmer with respect to the river, is 2 meters per second. Now the first part of the question says, if he heads in a direction that makes an angle theta with the flow direction, see how we have drawn this in the figure, the angle theta that the velocity of the swimmer with respect to the river makes with the river direction is theta, the flow of river is theta. This is slightly different from what we discussed in the theory of this particular topic, riverboat problem. There we took the angle theta with the direction AB. Here this angle theta is with the flow direction, so that this makes a difference in the way we will handle the question. So we are supposed to find out in this case the time that he takes to cross the river. That's the first part of the question, t, to cross the river. Then the next part of the question is find the shortest possible time to cross the river. T minimum is what we are supposed to find out. Okay. So for that we shall see what we can do. And then the next part of the question says, if the man has to reach the other shore at a point directly opposite to his starting point. So if he has to reach the point B, if he reaches the other shore somewhere else, because the velocity will be in some other direction, he will reach somewhere else, isn't it? So he has to walk down to this point B. Find the minimum distance that he has to walk. So if we assume that, let's say the man reaches the other shore at a point C over here, then he has to walk down to the point B. Understand that the distance BC is nothing but the horizontal drift, and when they ask us to find out the minimum distance that he has to walk, that essentially means that we are supposed to find out the minimum drift, right? So the time taken to cross the river, the minimum possible time to cross the river, and then the minimum drift. All the three things we are supposed to find out. In this particular case, if you look at it carefully, the way the figure is, do we understand that in this case the actual velocity of the swimmer, which we can get again from the definition of relative velocity, velocity of the swimmer with respect to the river will be velocity of the swimmer minus velocity of the river, and from here we get velocity of the swimmer as velocity of the swimmer with respect to the river plus the velocity of the river. Velocity of the swimmer with respect to the river is this velocity, and velocity of the river is this velocity. So we have to add these two to get the final velocity of the swimmer. See that this will come out like this. The actual velocity of the swimmer will be in a direction like this, and so that it will reach the other shore somewhere here. This will be the point C, right? Now from the given figure, can we write the expressions for the vector VSR and the vector VR if we assume that, let's say, this direction the flow of river is along the x-axis and perpendicular to that is the y-axis? Do we all see that we can write the vector velocity of the swimmer as VSR, which can be written in its component form as VSR, the magnitude of the speed velocity of the swimmer with respect to the river, into its components now. Can we write it as cos theta I cap plus sin theta j cap? What I have done here just now is I have split the vector VSR in its rectangular components along the x and the y axis, plus the velocity of the river VR can be written as velocity of the river itself along the I cap direction. The river is flowing along that direction, right? So, this is how we can write the expression for velocity of the swimmer. We can combine the I cap terms together to write this as VSR cos theta plus VR I cap plus VSR sin theta j cap. So, we get the two components of the actual velocity of the swimmer. This component is along the river, along the I cap direction, along the river flow, and this component of velocity is perpendicular to the river flow, right? Understand that it is this component of velocity of the swimmer which will help it cross the river, whereas this component of velocity of the swimmer which will help it take a displacement along the river, so create a drift, horizontal drift, right? So, now once we have understood all this, now we can look for the questions to be solved. The first part of the question where we have to find out the time taken to cross the river. Can we say the time taken will be the width of the river that has to be crossed divided by the speed of the river across the flow, isn't it? Which is this component of the speed, the one that helps it cross the river. So, it will be VSR sin theta. Displacement by the speed will give us the time, and we can now substitute the values. W is given to be 400 meters divided by VSR is given to be 2. So, 2 sin theta meters per second. So, from here we will get 200 by sin theta seconds, because theta is not given to us in the question. Our answer will come in terms of theta itself, right? So, this will be the time taken to cross the river. Now, the next part of the question is we have to minimize this time. We have to find out the minimum time. So, for that we can take the help of the expression that we have obtained above. This is the time, right, in terms of theta. When will this time be minimum? This time will be minimum when its denominator takes maximum value. That means sin theta is 1, right? So, can we say that t will be minimum when sin theta becomes 1? Sin theta is 1, which implies theta is 90 degrees, isn't it? Theta is 90 degrees here in the figure, means that VSR, the velocity of the swimmer with respect to the river, is along the direction AB. So, in this case the answer will be just 200 seconds, the minimum time. And now for the third part, we have to minimize the drift. We have to find out the minimum drift suffered by the swimmer, for which we first find out the drift. Recall how we find out the drift. The drift is nothing but the distance travelled along the river in the time in which the boat crosses the river. So, what is the velocity along the river flow? It is this velocity component. So, it will be velocity along the river VSR cos theta plus VR into the time that the person takes to cross the river, which in general the time is 200 by sin theta. So, this is the expression for drift that we are getting, and now we have to minimize this drift. So, we shall be using our basic method of minimizing the quantities by differentiating d with respect to the variable on which it depends, which in this case will be theta, and then putting it equal to 0. But before we differentiate it, let us just simplify this expression a little bit. Let us take the sin theta inside the bracket beneath both the terms, so that we get VSR cos theta by sin theta will be cot theta, right, plus VR into 1 by sin theta will be cosecant theta, multiplied by 200. This is what we are getting for d, and now let us differentiate this d. d by d theta, we have to differentiate this expression. Understand that VSR is a constant, VR is a constant, and this 200 is a constant. So, it is only these two terms that are to be differentiated. So, we will get VSR, differentiation of cot theta will be minus cosecant square theta, whereas the differentiation of cosecant theta will be minus cosecant theta cot theta, right. So, now what we can do is, in order to simplify this, and now we put this whole expression equal to 0, so that this 200 goes away on the other side, and we can take a cosecant theta also common from these two terms, and we are left with VSR, minus sign will also go away, VSR cosecant theta plus VR cot theta is equal to 0 is what we are getting. Now, we can simplify this expression to get our answer. See that cosecant theta can be written as sin theta, 1 by sin theta. So, this will become this plus VR cot theta will be cos theta by sin theta. So, once again we can take sin theta common out of the two terms, and that can also be taken on the other side. So, that we will be left with VSR plus VR cos theta is equal to 0 as our final expression, and this will give us cos theta is equal to minus VSR by VR, isn't it? Let us substitute the values for these two. VSR is 2, so it will be minus 2 by VR is 4. So, we will get cos theta as minus 1 by 2, for which implies theta is, cos is minus 1 by 2 when theta is 120 degrees, right. So, theta comes out to be 120 degrees. Understand that in the figure, theta is equal to 120 degree means the VSR value will be somewhere over here, which is okay. Our theta can take an obtuse value, right. We can just make it on the other side. So, once we get this value of theta, now we need to substitute this value back into the expression for d to get the minimum drift, right. So, we once again use this theta into, this implies the minimum d minimum will be d with theta is equal to 120 degrees, and now we substitute this value. So, we have d as VSR cos 120 plus VR into, outside we have 200 by sin 120. Now, we need to just solve this expression where we know that VSR is 2 and VR is 4. We can substitute these values as well. So, we will have 2 cos 120, recall it is minus 1 by 2, and plus VR which is 4. So, this is what we have inside the bracket, and outside we will have 200 by sin 120. Now, sin 120 is the same as sin 60, which is root 3 by 2. So, root 3 by 2 will go up, and when you solve this, this 2 will cancel out, 4 minus 1 will be 3, 3 into 400 by root 3, which will actually be 400 root 3 meters. This is your minimum drift.